All right, thank you for the introduction. Again, I'm Janel tayo. I'm also part of the e-mobility R&D group of UP-EEI, and I'm here more of to actually report the deliverables that we had for our DOST funded project entitled Design of Electric Boat for Inland Waterways to Address Urban Congestion. So these are my teammates for that project, and I'm going to report more of our outputs for that project. So the main motivation really for this project is that the shipping industry contributes 2.5% of GHG emissions worldwide, and the International Maritime Organization aims to lower this to net zero emissions by 2050. And one of the possible solutions for that is really the electrification of the fleet of marine passenger ferries. Why passenger ferries? Because passenger ferries are actually prime candidates for electrification because there is already a set route. Meron na tayong set route dun sa mga ginagamit natin na passenger ferries, meaning you already know or expect kung ano yung magiging performance and route ng ferry natin. And through this project, we actually explored retrofitting of existing passenger ferries, particularly in the Pasig River ferry system. This has 4 objectives, mainly to determine the potential for emission reduction, retrofitting design for each electrification configurations, estimate the energy demand through simulations before we actually spend money on buying equipment and on the retrofitting itself, and of course, to determine the techno-economic feasibility of the retrofitted design and the deployment of charging stations. So these are the framework or the steps that it took us to be able to evaluate each electrification configurations for the fleet of passenger ferries. As mentioned, we chose the Pasig River ferry system mainly because it's the most convenient location for us, and it already has the system in place in their Pasig River ferry fleet. So what we did was actually to gather the operational data from that location. So, for example, we were able to verify that the round-trip duration is 2 to 3 hours. There's an average docking time of 30 to 45 minutes. And the fleet size is actually 7 55-seater passenger ferries. Furthermore, we deployed surveyors so that we could get the real-time GPS data from the ferries and in turn output a voyage cycle that we can use in our simulations. And this is the actual voyage cycle that we were able to get, and also measure the fuel economy of the existing fleet. So what we measured actually is that the existing fleet has a fuel economy of 2 to 2.3 liters per kilometer. Aside from that, we also looked at the different accessible possible charging ports that we could actually deploy along the route of the Pasig River ferry. So these are the 4 locations that we saw would be most appropriate for the deployment of the charging stations, mainly because the ferry are actually spending their time on the docking, spending an average of at least 30 minutes of their docking time through these different stations. So the 3 electric propulsion configurations evaluated in this study is shown in this slide. First is the purely battery electric, wherein you're only getting your energy from the batteries. Second would be the diesel generator and electric motor. And third would be a hybrid of the battery and the generator. So most of the methodology that was used in this was actually from one of our key teammates, which is our naval architect, Cheryl Jokdo. And she actually introduced us in how we can model the ferry in order for us to determine the powering requirements. So the first step is actually to get the hydrostatic calculation. Through this, we were able to determine the hydrostatic characteristics such as displacement, wetted area, draft measurements, and center of buoyancy, we used the MaxSurf software and the Rhinoceros software, most commonly used by naval architects, to be able to do this. After which, we were able to simulate the component placements of the different electric configurations. So for this one, this is for the battery electric component placement. As you can see, the blue components over there are the AC motor and the battery bank. And then the diesel generator and electric motor component placement, wherein, if you can see the red box, that's the size of the diesel generator. And we actually used, through this, we actually used counterweights, remembering that we have to check the stability of the ferry also while we are placing the components. And for the hybrid one, the counterweights, previously with the blue color, was actually replaced with battery banks. So all of these modifications were taken into consideration in the estimation of the weight per configuration. And also, for all of the configurations, we assumed that the ferry is operating under full load conditions, meaning 55 passengers plus 3 crew members. And upon assigning the weights and placement of the electric propulsion system within the hull, stability calculations were done using MaxSurf and ANSYS Aqua software to determine the metacentric height per configuration, which provides an evaluation point for the stability. According to the International Maritime Organization, the recommended metacentric height, or the GM value, for inland ferry is between 0.5 meters to 1.5 meters. The powering requirements in kilowatts versus the different speeds of operations were determined after the modifications were considered as shown in this graph by computing for the total resistance, including the frictional, air, and wave-making components. The red line represents the generator and hybrid case, which show that the highest powering requirements compared to the blue curve, which is the battery electric case. So we also use this powering requirements and the 45 kilometers reference voyage cycle that we were able to gather during the data gathering phase to be able to estimate the fuel consumption or the energy consumption through MATLAB Simulink. And the results show that for the base case model, our simulated fuel consumption was found to be 104 liters, equivalent to around 301 kilowatt hours of equivalent energy. And the resulting simulated fuel economy is actually 2.3 liters of consumption per kilometer, which actually goes back to what we gathered on the actual fuel usage of the ferry. So our validated data and the simulated data actually matched. And for the battery electric case, there is an increase in the weight, in the total mass, therefore also an increase in the wetted surface area and an increase in the power. And what we measured to be the simulated energy economy is 7.3 kilowatt hours per kilometer. And then for the diesel and hybrid, since they have the same mass and the same hydrostatic calculations, these are the resulting values. So all of these values, we are going to input in the techno-economic analysis in order to determine the cost of energy. So this is the final specifications of our proposed retrofitting for the battery electric ferry. And actually, we also simulated what it would look like if we deploy 4 charging stations, 1 in Napindan, 2 in Guadalupe, and 1 in Escolta, with 7 retrofitted battery electric ferries, so that we can see if the operations will be feasible. So this video shows where the electric ferries will be charging, where they are intersecting, and we have determined that at the Guadalupe station, there will be at least 2 simultaneous charging transactions. So after which, all of those inputs that we were able to verify and the simulations that we were able to generate, we now use as inputs in our techno-economic study, wherein the voyage cycle, the energy estimations, and the fleet management model that we did, we assigned cost estimates. For the capital cost, given that there are 7 retrofitted battery electric ferries, there are 3 key locations for the charging stations with 4 total charging points, this would be the capital cost. This is considering that there are still 13 locations, 13 stations along the Pasig River ferry route. So as you can see, the battery electric ferry or the battery electric case has the highest capital cost. And the lowest capital cost is still the diesel ferry. For the operations and maintenance, so the key assumptions here is that it's 20 years of service life, 7 ferries, and then we use the simulated values of the fuel economy and the energy economy, and then the personnel is proportional to the number of charging infrastructure, or so that means that when you have the diesel generator, the hybrid and the battery electric, there would actually be more personnel that you have to employ. And as you can see here, that even with complete replacement of the batteries and replacement of the generators, shown by the peaks in the graph, the battery electric ferry, the orange pala yun, di pala red, has still the lowest O&M among the different cases. And this also translates to the emissions. Pinakamababa yung emissions for the battery electric compared to the hybrid, the generator, and of course, pinakamataas yung sa diesel ferry. And this also translates to the total cost of ownership, wherein the diesel ferry, the first one here, has the highest cost, and battery electric has the lower cost, greatly dictated by the pink color, which is actually the cost of energy, and the green color, which is the cost of emissions. Yan, so tama lang. So this is our conclusion. Battery electric had the least energy economy, least displacement and mass, and the lowest draft measurement out of the 3 configurations. And this also has the least total cost of ownership despite having the highest capital cost. But there's also one thing that we realized during the conduct of the study. We are greatly limited by the existing design of the ferry. So ferry retrofitting is generally feasible but may not be the most efficient solution due to the limitations in space. For example, the Pasig River ferry actually uses a monohull design, which is not necessarily the best design for a shallow river. So we conclude that hull shape and type also contributes to the design efficiency. So that's all. Thank you.
Thank you, Ms. Janel tayo. Are there any questions from the audience? I guess I have one question. Given the charging and powertrain of land vehicles, what are the major difficulties introduced by having the ferry in the water? Is that too different from the charging system and powertrain system of a land vehicle?
Thank you for that question. Actually, there is a great difference. Number one being the cost of the equipment. Since we are talking about higher IP ratings compared to land-based charging stations, we definitely see that the deployment of charging stations in river systems, in shore systems would be more expensive compared to the land-based systems and more subjected to safety regulations.
I'm just curious about the response of the LGUs along the Pasig River. How are they helping, basically?
Actually, MMDA has been a very good partner in this. We are actually already at the second phase of this study wherein we're going to prototype the ferry. And there is already design in place. There's already a definite charging location in place. So they are closely working with us and they are very excited with the project.
Are there any other questions? If none, I would like to thank Ms. Rovinna Janel tayo. and I would like to give this certificate of appreciation for sharing their invaluable insight and work on a methodology on the techno-economic evaluation of electrification of an inland waterway passenger ferry during the NISCON 2024 conference, signed by Dr. Luandro Tria.